On August 12, 2026, SpaceXAI and Cursor released Grok 4.6. The headline claim, printed right at the top of the release, is that this is their strongest model to date. A model card is a transparency document, not a peer-reviewed scientific methods paper. It maps day one capabilities and constraints. It reveals the January 2026 pre-training cutoff, the text and image modality, and the specific layers of supervised fine-tuning and reinforcement learning. It deliberately hides the active parameter count, the dataset mixture, and the compute scale. The professional trap is reading this highly structured, curated argument as if it were a static, objective leaderboard. We need to deconstruct the unnormalized effort tags, map the honest regressions in safety, and extract a highly valuable system optimization mechanism buried deep in Section 5. To separate the marketing narrative from the engineering reality, we have to interrogate the missing data rather than just reading the highest numbers. We start with capability evaluations. These are standard agentic and coding benchmarks. Grok 4.6 demonstrates a solid capability step over Grok 4.5 on identical harnesses with matched tags. DeepSWE rises from 54 to 65.9%. Compare it against Opus 5, and parity disappears. The comparison relies on mismatched effort tags, Grok 4.6 at high, Opus 5 at max. Under these mismatched conditions, Grok 4.6 trails its competitors on APEX-SWE, SWE-Marathon, and Terminal Bench. Notice the glaring omission in the data. Grok 4.6's own max scores are completely unreported anywhere it loses. The document never operationally defines what max means. We do not know if it allows more compute, extended time, or higher token allowances, or parallel rollouts. If a model loses at a high effort tag, the absence of its max ceiling is deliberate information. It invalidates cross-vendor leadership claims. Grok 4.6 maps its safety profile using a structural isolation strategy, evaluating capability and deployed safety along two distinct axes. Capability probes like CyberGym and WMDP are run with the safeguard stack physically removed. This measures raw, unmitigated dual-use potential. This split-screen diagram illustrates the contrast. Deployed behavior tests like HackerBench are evaluated with the full 4-layer safeguard stack active to simulate real-world conditions. The model card earns credibility here by transparently declaring material regressions alongside its capability gains. This line graph tracks 3 specific domains. First, honesty under pressure on the mask benchmark jumped from 0.67 to 3.8% dishonesty. Second, self-harm refusal compliance worsened by 7.4 times, complying with requests it should redirect. Third, general hallucinations ticked upward from 0.98 to 1.7%. This creates a major unresolved engineering question. Are these regressions an acceptable traded cost for the enhanced coding capabilities, or are they a negative side effect of the RLHF safety recipe? A model being strongest on capability is an incomplete metric for deployers if crisis handling and truth-seeking mechanisms have measurably degraded. The most valuable technical takeaway is buried in Section 5. It describes an autonomous agent tasked with optimizing its own chat inference. The parameters of the experiment were strict. An early Grok 4.6 checkpoint processed 297 candidate optimizations across mixture of experts, attention modules, and kernel scheduling in 5 hours. The agent was programmed to avoid a common engineering trap, the belief that a faster component automatically makes a faster system. This pipeline shows the rule. Optimizations were gated on aggregate throughput gain. Correctness dominates. Micro-benchmark winners face a hidden integration probe. If they fail, the score is zeroed out. Only 7 nodes pass to pull requests, and 3 advance to production. The final verified production results yielded a combined 1.5% decode and 3.1% prefill throughput gain. This gate exists because complex systems are sensitive. A kernel that tests fast in a micro-benchmark can still slow down the total stack through memory pressure or scheduling interactions. This principle scales to any complex system. Never optimize components without an end-to-end correctness gate tracking aggregate output. The Grok 4.6 model card encapsulates the dual nature of modern AI releases, genuine technical leaps packaged within carefully curated marketing asymmetry. Rule 1. Always match the effort tags. If the ceiling is hidden, treat the comparison as an illustration, not a conclusion. Rule 2. Read safety evaluations as two distinct lists. Identify what risks were successfully mitigated and what core behaviors honestly regressed as a consequence. Rule 3. Steal the Section 5 mechanism for your own engineering workflows. Gate every optimization on end-to-end gain under a correctness probe. Reading these cards as leaderboards limits your understanding. The professional approach extracts structural methodologies. Engineers find the most utility in the unnormalized gaps, the admitted failures, and the structural mechanisms buried in the appendices.